You can start. Don't worry. Yes.
Okay. So I wrote something. Okay, the claim is that if you consider, a spin Hamiltonian which has periodic boundary condition, then what you find after Jordan-Witten transformation, you can write it in this way, where S is the product of order sigma Z, and now you have two different quadratic forms of fermions, which are characterized by two matrices, H minus and H plus. Okay? What's the shape of these matrices? Because after all, we are considering a translation invariant model, so they should be sufficiently simple. Those things there. And this is what you find. So you see that these matrices have a block structure. They are 2 by 2 structure. And why, first of all, they are 2 by 2? Because if you now look at the definition of the Jordan-Witten transformation, you see that the Pauli matrices at a given site are defined in terms of two Majorana fermions, 2L minus 1 and 2L. Right? So this is why translation values you can see only if you consider 2 by 2 blocks, okay, of Majorana fermions. And this is why this matrix H plus, and H minus are the block structure. Then periodicity, you see the periodicity of the model in the fact that all the blocks are the same along the block diagonal. So it's like this. So it's like, I don't know if you know Toplitz's operator or circulant matrix, you know, I don't know. But anyway, so what you find is that all the elements on the block diagonals are equal. Where are the boundary conditions? The boundary conditions are here. You see, when you consider, for example, the second diagonal, you have a missing element here, which is here, if you consider periodic boundary condition on the rows and columns of the matrix. But now the question is this really equal to this? And now the answer depends on the S, on whether you are considered H minus or H plus. For this term of the Hamiltonian, H plus, this is exactly equal to this. These two terms are identical, like these two terms. So this is called a block. This is a block circulant matrix for H plus.
The size is 12 by 12.
The size is 12 by 12. This is a 12 by 12 by 12 block circulant matrix. Okay? There are other properties. The other properties are that it's a purely imaginary matrix. Purely imaginary. And it's antisymmetric. And these are the most general properties of this matrix. Whatever you do, whatever Hamiltonian you consider, you will have that H plus is a 12 by 12 block circular matrix, which is pure imaginary and antisymmetric. From these two conditions implies that it's also Hermitian. Okay? The Hamiltonian is Hermitian, I assume that.
We have the explicit expression for this matrix for, let's say, the X model?
Yes, we can. We will work out somehow. But okay, now we'll just tell you the structure of the matrix. This is why I call this algebraic approach, because we are really just looking at the structure of the matrices of the This is for H plus. What happens when you consider H minus? H minus again has the same form in the bulk with the same elements, so it doesn't change. Okay? The only difference is that these terms here have anti-periodic boundary conditions. So it means that now if you consider minus here, then here you have a minus sign, here and here. And you will have the minus sign when you consider all the other diagonal, minus sign here, and so on. So in other words, you have, if you impose periodic boundary conditions on the fermions, when you express them in terms of the Majorana fermions, you have an Hamiltonian which is split in two different sectors. one sector where this operator S has eigenvalue 1, and one sector where this operator has eigenvalue is minus 1. In the sector where this is equal to 1, then the boundary condition, if you want, on the fermions are antiperiodic. They take a minus sign. Antiperiodic means antiperiodic. Okay, antiperiodic boundary conditions means, in particular for the fermions, that A12 plus 2 is equal to minus A12. Okay, this means antiperiodic. With periodic instead of the plus sign. Or for the spin of it. Okay?
Minus C.
Thanks. Yes. Okay, so these matrices are so well structured that we know everything about them. Okay, they are very, in particular, what the fundamental property of these matrices is that they can be solved, they can be written in a simple form when in the Fourier transform, which is clear because you see that here there is some periodicity in the Hamiltonian. So every time there is some translation invariance, your problem will be, you can expect that your problem will have a simpler form in the Fourier space. So, and if you now try to write this block matrix, no, in a Fourier basis, this is what you find. So first of all, you have to take into account that this is a block matrix. So in order to, you need two indices, okay, for each side. You need the index of the block. This is the block. And this is an index inside the block. Internal index. So if you now rewrite the matrix element in this form, then you find that clearly you have this kind of simple expression for the index of the blocks, so they can be written as the sum in the Fourier space of all some momenta k that we will see in a moment of the phases times a 2 by 2 matrix in the internal degrees of freedom, I and J. And you see that depending on whether you consider the matrix with a plus sign or minus sign, then here you have different condition on the momenta allowed. So in particular for the periodic case, you have the condition that e to the ILK should be equal to 1, which means that the momenta are quantized like 2 pi over capital L. In the other case, you have that this should be equal to minus 1. So the quantization is different. So this means in one case, that's right here. In one case for S equal 1, it means that the fermions belong to 2 pi over capital L to 4 pi over capital L, and so on. If S is equal to minus 1, case that is that in pi over capital L, 3 pi over capital L, and so on. So the only difference is in the set of momenta you have to consider. Because these sets are such that they realize the correct boundary conditions. Okay? But nevertheless, the form is exactly the same. And this 2 by 2 matrix here is common to both matrices, H plus and H minus. It's the same matrix. It doesn't depend on S. You should be at least positively surprised of this, because we started with a spin chain Hamiltonian with a 12 by 12 degrees of freedom matrices, if you imagine. So it's an exponentially larger number of degrees of freedom in L. Using this, we brought it in something that essentially has a dimension L times L, 12 times 12. So it's completely characterized by this matrix. But now what I'm telling you, if you use also that the system is periodic, we can describe everything in terms of a 2 by 2 matrix. Okay? In a common language, because okay, this is a bit, this is the part that I was telling you is a formalism, the algebraic formalism. In the standard language, what people say is that you first step is to write your problem in the first space, which is encoded in this part, and then you perform a so-called Bogoliubov transformation. The Bogoliubov transformation is a transformation that diagonalizes this matrix, essentially. Why we have to do that? Now I will tell you. Tell you some properties of block circular matrices of the spore. And one property is that when you multiply 2 block circular matrices, so let's assume that you have 2 matrices, one is A, S, okay, and then you multiply by BS. And then, okay, this is equal to, if you use that representation, like 1 over L sum over K with the correct quantization, e to the I, K, L minus N. Okay, this is I have to put indices here. So, if you write this element L, 2L minus 1 plus I to N minus 1 plus K, then this would be L minus L prime sum over L prime and J prime 1 over L, right, the first matrix, and then you have here A of E, K, I, J prime, then here you will have the other matrix, which is 1 over L, sum of K with the same boundary conditions, E to the I, K, L minus L prime, and then you have here B of K, and then you have a J prime J, F prime minus N. This is what you have to compute, and then what you find, simply you will find it by summing first over L prime. This is equal to the 1 over L sum over K as of E to the I, K, L minus N, A, E to the I, K, B, to the product of the two matrices, I, J. This is it's a very strong property, so I'm saying that they are close under multiplication. So if you multiply a block circular matrix or anti-block circular matrix, they remain either block circular or anti-block circular, and this is called in the German symbol of the matrix. So the symbol simply transforms as the product of the symbols. This is the most important property that we are going to use. So this is the property of the matrices. Now I give you a property of quadratic operators, which is important, and the property is the following. If you have now 2 quadratic operators written in this way, so you have A, A, S, A, and you consider the commutator of 1 of 4. The commutator of this with another operator of the same form, as A, we now characterize with the matrix B. This has the same form. It's 1 over 4 A times commutator A S B S A. So it means that not only the matrix, the blocks equal matrix are closed under multiplication, but also if you now consider the quadratic form of fermions, and if you consider commutators, then they are closed under commutations. And the matrix is characterized by the commutator is simply given by the commutator of the matrices. Now you can use this result here, you use it here, and then you realize that everything can be encoded in the symbol. Because now when you consider the commutator of two quadratic form, then this corresponds to consider the commutator of the symbols.
Instead, if you do a commutator of two symbols with opposite, let's say S,
Then no.
that is 0, or there's no simple form?
You can work out. It's not.
It was just.
But I don't think that you can simplify it a lot.
Because there you have the two cases which have different.
Right.
So I was.
You are right. I'm not right.
Okay.
Because as you see, these two, we have two different boundary conditions there. But we have that they are multiplied by the projectors. So now imagine that you consider the commutator between the Hamiltonian and another operator of the same form. Because of the projectors, you don't mix the two sectors.
Yeah. I was
so
just
you are
wondering.
always in the same set. Let's write also this result. Again, this is for the quadratic form, so we generalize even more, and now we consider the commutator between two operators now of that form, which I call A and B. These are spin operators. These are 2 to the L. They act on a 2. They are 2 to the L times 2 to the L from matrix, so they act on the space of the spins. So now if you consider the commutator here, then the commutator here, and you written as again the projectors. And then you have the commutator of the two terms, like this. So it will be 1 over 4, A, and commutator between the corresponding matrices, A minus A plus 1 minus S over 2, 1, 4, A plus B plus A. So every time that you are interested to the commutator between two non-interacting operators, A and B, which have this form, yeah, then you see that in the end it can be reduced to it remains of the same form, and the commutator here, if you consider the boundary condition, can be expressed in terms of the commutators of the symbol. Okay. Now, I think I should establish a connection between what is standard. So if you want to diagonalize this Hamiltonian, what do you do in this formula? Because maybe now I can do it confusing.
This H plus and H minus reminds me of free fermion Hamiltonian because it has a diagonal kind of chemical potential term, then upper diagonal kinetic term. Can I say that H plus and H minus is a kind of fictitious Hamiltonians of some system?
Well, if you want, yes, but what do you mean that it's like the free fermion? Because you are saying the same, actually. These are the Hamiltonians that characterize also a free fermion system. When you imagine that there is a chemical potential open term, then you can imagine to the right, but they are the same objects. exactly the same, essentially the same objects.
Okay.
The only difference is that now I express everything in terms of Majorana fermions to consider more general class of moments. Okay. So let's assume now that we want to diagonalize the model. Okay. What do we do? Okay. First of all, it's okay. I think it's convenient to show you some property. Now let's consider another properties of this matrices. We consider the commutator between an operator of this form, again, a quadratic form of fermions, A S A, and not commutator, and something written in this form, a linear combination of Majorana fermions. So what happens if you do this? Is you can prove by imagine how do you do this? You write this in terms of the indices. You have to sum over the index L over the index N, this matrix, and then you have another operator on Majorana fermions here with another index. Then you try to move this operator to the left, and you use the anti-commutation relations. What you find in the end is that this is equal to A S W. Okay. So first of all, note that when you consider a commutator between a quadratic form and a single linear combination of fermions, you obtain something which is a single fermion. And then, okay, well, this is the result that you find. Okay, now, so in particular, let's assume that this W, let's consider the W which is an eigenstate of A. So let's imagine that now we consider a W such that A S W is equal to some eigenvalue, epsilon W. So let's assume I'm diagonalizing this matrix in a sense. Then what happens? What happens is that, okay, first of all we can take in the conjugate of this expression. Now remember that these block circular matrices are Hermitian, so the eigenvalues are real, but they are also purely imaginary. So if I take the conjugate here, I get a minus sign for the matrix because it's purely imaginary. So I get minus AS W star is equal to epsilon W star. I'm just taking the conjugate. I know the conjugate transpose, just the conjugate of it. Now if I apply the minus sign here, so this means that if we have an eigenvector with eigenvalues epsilon, we can immediately find eigenvector with eigenvalues minus epsilon, which is just the conjugate. That's proper. Then okay, let's now imagine that we know a state, an eigenstate of this quadratic form. So let's assume that, for example, you know the ground state for some reason. So now, so you have 1/4 A as A, and then I am giving you the ground state. Is equal to energy ground state times phi. And now let's imagine to include here a linear combination of Majorana fermions corresponding to this eigenstate. What happens? So what happens is now I compute 1 over 4 AS A times my W A W. Now, here, what can I do? I can commute this. And when I commute it, I obtain exactly this result. But now, this is an eigenstate, so I obtain epsilon. Now, okay, I do the steps. So this is equal to the commutator between 1 over 4 AS AW plus AW 1 over 4 AS A applied to the state that I gave you. Now this commutator, it would be equal to AS let's write the step. So this is equal to ASW plus W times this. And now notice that this operator applied to the state is just the ground state, I told you. So this is equal to plus energy ground state or applied to the vacuum. But now ASW, W is chosen to be is an eigenstate. So this should be equal to epsilon AW, and here there is also AW here. So we have it is equal to epsilon plus energy ground state applied to the ground state. Now, the energy of the ground state is the minimal energy that you can have. Realize here, I'm just saying that this is also an eigenstate of the Hamiltonian with this new eigenvalue. But now, because this is a ground state, it means that this epsilon cannot be negative. Or if it's negative, this state should be annihilated by this operator. And this is in fact what defines your ground state. The ground state is is a state such that is annihilated by all this linear combination with a negative eigenvalue. Instead, every time that you put here a linear combination with a positive eigenvalue epsilon, then you can reach an excel state of the model. So the claim that you can now imagine is that this linear combination are nothing but what is called the Bolivar fermions that diagonalize the Hamiltonian. And in particular, if you find if epsilon is larger than 0, then you can write this as you can just define it as the creation operator with energy epsilon. If instead you are considering something which are epsilon smaller than 0, then this means that this is the annihilation operator. So you have that B, you have to define B, which is defined like this, and it corresponds again to an excitation with energy epsilon. So it's the same kind of excitation, but in one case is the operator that destroys the excitation, in one case is the one that creates the excitation. So within this formalism, what you see is that the excitation energies are the eigenvalues of this block circular magnet. Okay? So, and the ground state is defined as the vacuum of all these fermions that you can define. But this is just to establish the connection with the standard technique to diagonalize.
For this part where you construct the many-body eigenstates, in fact, you don't need the translation invariant.
Yeah, I don't need it. Yeah, this is completely general, right?
Okay.
I need translation invariance when now I'm trying to rewrite the excitation energies in a simple form. Then I will use now translation invariance. But so far, that's true. All this part of the blackboard is completely general, even for non-translation invariant, non-interacting. Okay. Yeah, so I wasn't trying to write it, but now maybe I will write it. So let's assume now we want to compute this excitation energies of our model. How do you do it? We have to diagonalize this matrix, this block circular matrix. I told you that this is known. This is very well known. So I just tell you the solution. Okay. So you have your AS, which was block anti-circular. Now we find the eigenvectors. And my claim is that the eigenvectors have the form. Yes, have the form sum L. AS times B. We want to solve this epsilon W. So we write the components, and then we have A S 12 minus 1 plus I 12 to L prime minus 1 plus I prime, sum over L prime I prime. And then you have your W of 2L prime minus 1 plus I prime. This is what you want to do. You want to impose that is equal to epsilon 12 minus 1 plus I. And the claim is that this object here, W 12 minus 1 plus I, is equal to the sum over n of e to the I n and k times the vector v, vector v I, okay, where k is such that e to the I at k is equal to s, and v, this 2 by 2, not 2-dimensional vector, small vector, is the eigenstate of of the symbol of the operator. So you have A, which I called before A, AB is equal to epsilon, okay, epsilon, okay. So what I mean is that you can find for each k here, satisfy this condition, you find an eigenvector of this matrix, and the eigenvector of this form. So you have just the eigenvector expressed in Fourier transform. And what you have is that the excitation energies, this is the most important part of this, that are just given by the eigenvectors of the symbol. So everything, we start with the problem of a spin lattice, so 2L times 2L eventual problems, and if you want, we are interested in the excitation energies, then what we have to do is to diagonalize a 2x2 matrix.
Sorry, but then, I mean, you can rewrite the Hamiltonian in the K space, and that space should be just sum of
Yes.
the symbols.
Exactly. Well, if you do that, which is essentially what we did in
yeah.
right way, what you have here, you will have terms that couple k with minus k with k, and whatever. And then you try to diagonalize in this space k minus k. This is the 2 by 2. This is the symbol. The symbol is the matrix that connects the momentum k with momentum minus k when you write momentum. That connects. Okay, when you use that point of view, you rewrite the Hamiltonian in the form of terms like this. So you can have this. You can have a term like theta k, theta minus k, and you can have ck, c minus k usually. But now you see this is not diagonal. This is not yet diagonal. This term is diagonal. These are not. So you want to diagonalize this part. In order to diagonalize it, you have a two-dimensional space which corresponds to k minus k, which is essentially related to the symbol. So it's this is just a Bogoliubov transformation. We are just I told you at the beginning. This is just a different way to call everything, but it's standard. Why am I doing this? One of the reasons is that now, first of all, in this way, it's very simple to find the operator that commute with the Hamiltonian. So let's start with this. Because I told you that all this commutator between this quadratic form, okay, first of all, between non-interacting operators, can be reconduced to commutator to quadratic form of Fermi's. And then this commutator between quadratic forms are reduced to commutator of block circular matrices. The commutator now using the periodic boundary condition. The commutator of block circular matrices are traced back to commutator of the symbols. So now imagine that you are interested in finding operators now here, conservation laws. Then want to compute conservation laws of the model. So the conservation laws are the operator that commute with the Hamiltonian. So we want to find Q such that HQ is equal to 0. So there is a preliminary assumption. Let's say that let's focus on operators that are non-interacting, like the Hamiltonian. Okay, so we focus on that particular class of operators. Now the commutator between H and Q, if it's equal to 0, this implies that the commutator between the block of circular matrices characterizing the two operators should be equal to 0. Otherwise, you will find something which is non-zero. But now the commutator between the block circular matrices can be written in terms of the commutator of the symbols. So it also means that the symbols characterizing the two block circular matrices should commute between y and r. So we start with this is an hard problem, general in physics, finding operator commute with another operator. And in interactive model, there are very complex formalism to obtain this operator. So in this simple case of non-interacting spinal chains, we can really reduce it to find the 2 by 2 matrices that commute with a given matrix. What are these matrices that commute with a 2 by 2 matrix? Okay, before doing that, I just want to tell you two properties of the symbol, because I forgot. Because when I define the block circular matrices, I told you that they are pure imaginary, antisymmetric, and rotation field. So if you now rewrite them in terms of the symbol, then you realize that the symbol is not satisfies some properties. In particular, what you have is that H of first of all is Hermitian. So it's a Hermitian matrix. And moreover, what you find is that H, if you consider the transpose of the symbol, is equal to minus H of e to the minus ik. Okay, these are just two properties I forgot to to mention before, that follows from the block circular matrix. Okay, but now let's imagine you have just this 2 by 2 matrix. This H, so H of e to the I k can be something, okay, with 4 elements here. And you want to find all the matrices that commute with this 2 by 2 matrix. So there is a trivial matrix that always commutes with all the matrices, which is the identity. So we have one possibility is that Q could be something proportional to the identity, the 2 by 2 identity. Then there is another matrix that always commutes with H, which is itself. Okay, so something times H. Can you find more independent object matrices that commute with a 2 by 2 matrix? We already, let's assume that the H is not identity, otherwise these are the same. Let's assume H is different from the identity. Can you find another matrix that commute with a 2 by 2 matrix? We already found 2 of them. The answer is no. Okay? The answer is no, because if you imagine to diagonalize H, then it's diagonal. So you have the space, the only matrices commuting with H are just the 2 projector on the 2 subspace. You have just 2 independent, possible independent matrices commuting with it. So in other words, it means that if you write Q, so this is the most general form for Q in our simple case. So a generic conservation law should have something proportional to the identity Q, something proportional to the symbol of the Hamiltonian. Now, okay, we must be careful about this condition that this is why I wrote now, because well, this something is not arbitrary, because still the symbol should satisfy its properties. So what happens is that H already satisfies its properties. So here you can put almost anything. The only thing you must be careful is that it cannot be odd when you invert k minus k. So what happens is that here you can only put some even function of k. Okay? So here, let's just try some coefficient, C2 of k, where C2 of k equals C2 or minus k. So you can check that this term, if H satisfies this property, also this term satisfies this property. Okay? What about this term here? This term here, okay, the identity is already a Hermitian. So the first condition is trivial. Fine. The early first condition just tells us that this should be real. Now let's consider this other condition, and it's about the transpose. The transpose should be odd. So it brings k minus k with a minus sign. So if you here you put the C1 of k, what you have is that C1 of k should be equal to minus C1 or minus k. This is the most general symbol of this is the symbol of the most general non-interacting operator computed with H. Okay. Still, okay, we didn't we didn't mention any locality properties now. So far I am just constructing some operators I commute with the Hamiltonian. I'm just telling you that this is the most general form of the operator for the operators. But now last time I told you we should be interested in the local ones. So how can I see here locality? And for this we have to go back to the definition of the block circular matrix in Fourier space. because I wrote something like AS the element to L minus 1 plus I to L minus 1 plus J was 1 over L, sum over the momenta, of E to the I L minus N K, and then here you have the symbol of A. The element Ij. Now you want this matrix appear in the fermionic Hamiltonian as the matrix that connect to Majorana fermions. Okay, so remember the structure of the matrix. That this you have block structure. Okay, and then you imagine that this appear like here you should have a vector consisting made of all the Majorana fermions on one side, A1, A2L, and then you have A1, A2L. So the central part, you understand, this is just a scalar product. What I wrote before A, what this is, what I wrote before A dot A S A. What I meant before. So it's a scalar product between this vector, consisting of Majorana fermions, and this matrix acting on this vector. So now, if you look at this operator, you realize that all the terms on the diagonal connect Majorana fermions which are close by indices. Okay? The more you move from the main diagonal, and the more the indices spread become different. But if you now remember the mapping between the Majorana fermions and the spins, then you realize that the range of the Majorana fermions there is a one-to-one correspondence, essentially with the range of the spins. So in other words, what I'm saying is that all the contribution from this, from the diagonal, which are not the main diagonal, whatever, correspond to operators which have a larger and larger range. If you move in this direction, it corresponds to operator which spread out, which have a larger support. So in order to consider local operator, we should have something which is a local operator should have a corresponding matrix with a finite number of non-zero diagonal. Because if you have the more far away you go, and the larger becomes the support. If you count it, then in the support is finite, and the operator is local. Local, remember, means that the operator acts only on a part of the system, small part of the system. This is our in shape. Local operator means that here it does something here and not elsewhere. Okay.
Somehow the sub-region you want to keep it fixed, not scaling with system size.
Exactly. Fixing, you want to fix the region, and also here I'm fixing the diagonal,
yeah.
if you want, how many diagonals I want to keep, and then if I want, I take the thermodynamic in after. So if I do this, so I put 0 here and here. So I'm sure that I consider local operators. But what does it mean in this language? Since this is just a Fourier transform along this direction, that is L minus n, it simply means that when you consider the Fourier coefficient here, you have only a finite number of Fourier coefficients. The only way to put some 0 here is to do things in such a way that the I or the Fourier coefficients are 0. In other words, the symbol cannot have arbitrarily large free coefficients. They can be written in terms of something like some coefficient a1, let's say, times e to the ik plus a2 e to the 2 ik plus, okay, that would be terms a1 bar e to the minus ik plus e to the 2 bar e to the minus 2 ik, and then stop. So you can consider arbitrary higher free coefficient. So you have a defined number of them. This is enough to ensure that the operator is local. So we, is it clear? Or, okay. Now we go back here. So what's the only requirement here to have local conservation laws? Okay, we are, here we identify two families, if you want. One family corresponds to this part, the other family to the other symbol, or you can mix them, you can do whatever as you prefer, but generally people present them into, say, as two separate families. Now here, well, this constraint of locality means that this coefficient Cu1 must have a finite number of real coefficients. It should be odd, so it can, for example, be sine of k, sine of 2k, sine of 3k. This sequence, indeed, generates all the possible local conservation laws associated with this family. So C2 for locality implies that C2 of k is equal to some sine of nk, sine of nk, or linear combination of sines up to a given n.
But what about upper right coefficient and lower left?
Upper right, yeah?
Yes.
These are
They somehow affect on locality.
yeah, but this diagonal it ends here. The diagonal here, as I show in the previous speech when I was drawing the block circle, because it's a block circle matrix. If there is an element here, there should be also an element here. So there will be a part of the diagonal here.
Okay.
Related to the boundary condition.
Okay.
So here you have sine of k. What about the other term? H, by definition, because we started with a local Hamiltonian, so H was already consisting of a finite number of real coefficients. If you want to preserve this property, and C2 should be even, then C1, sorry, should be even. No, okay, this was C1. So C2 should be even, so we can choose, for example, cosine of n.
N is something.
This is any integer that any integer.
Okay.
But it is an integer which is independent of the system size. So you fix the index, and then if you are interested in the thermodynamic properties, then you keep fixing n. You consider the limit of capital L equals to infinity. N is fixed.
N is L minus M.
Repeat.
There is a momenta L minus M that defines the distance from the main diagonal.
Yes, exactly. Yes, it's like that. Yes, exactly. It's related to the difference of the indices. So if you consider sine of nk, what will happen is that it will be non-zero only on two diagonals, here and here, at a distance which is proportional to n. This distance will be proportional to n. Here you will have, for this operator with sine and cosine, what you have is that they have this structure. Here they have zero inside. They are not zero along two diagonals, and they are zero outside. And they complete the space of all the local operators, because with them you can construct whatever you want for the other operator with them. Other questions? So what do we use here? Did we use so far? That, okay. First of all, I assume that the Hamiltonian is one side shift invariant. It was translation invariant. I sum over all the terms. Then I assume periodic boundary conditions, and assume, okay, there was a non-interacting spin chain Hamiltonian. Given that, I could write all the conservation laws of the model without even specifying the model. I'm sorry, I promise you to show you an explicit example, but okay, I will do in a moment. And it's completely okay. It's completely general. Yeah.
Sorry, when you say non-interacting, can we now be precise about what we mean in this context?
Non-interacting in this context means that I've been able to map the model to a quadratic form of fairness.
So that means we select from the set of sigma couples you described at the start of the lecture. That's the definition of non-interacting so far.
In this context, yes. Okay, if you are able to bring to map your system in free bosons or free fermions, and this is what here we can do, because if you complete the diagonalization, then it becomes just a free fermions for this model, and if in other models you have free bosons, so that this is what we call the non-interacting. So it's something generally you don't see immediately from the terms in the spins.
Yeah, that doesn't mean that the spin are not interacting.
Indeed, they are interacting. And indeed, people, some community called it interaction when you have also between spins. So then it's more related to the fact that you can solve the model, and also that there is a very strong structure about the energy levels, for example, that all the energies can be written as a sum of capital L excitation energies. And this is so strong that it is true only in non-interacting model by energy. And okay, other questions?
One question: this algebraic method is then useful, for example, to compute is the technique used to compute correlation function of the things that involve the string?
Okay, in that case, I don't think so. It's not really useful for that.
But also in that case, there is some sort of matrix structure, but it's not the same.
It's not the same. Okay, what I'm saying, okay, in order to compute correlation, it's always more convenient to work with Majorana fermions. Okay. So there is a common path, something which is convenient. Yeah. And but then, okay, I think that this formalism is not particularly useful for that. What is useful is for to compute the conservation law. This is extremely useful because we don't. We can solve this problem in general without using without having to compute commutative within operators, spin operators. It would be more complicated. And another reason why this is convenient, whether I want to present things in this way, is that it's easy to compute the time evolution of your state. Both the time evolution to take the thermodynamic limit, the infinite time limit, and also thermodynamic limit. And it's easy to check whether what you obtain is a GG. So you can prove using this formula in a simple way that in the limit of infinite time you end up with a GG. Okay, and this is what I want to do. And I think I'm not sure. Maybe instead of doing this, because it's something I should begin, it's more useful to show an example. Okay, for example, consider the Bayesian model. Standard example. So, Hamiltonian Bayesian model. Sum over L, sigma x, sigma L plus 1x plus h, sigma z. Now, we carry out the general linear transformation. This is equal to minus j sum over L, and here there is minus I a 12, A 2L plus 1 plus I H A 2L minus 1 A 2L. This is what you find if you apply the general linear transformation. Now, I want to anti-symmetrize these terms because I want to use that the Majorana terms have anti-commute between each other. So I want to write in an explicit anti-symmetric form. So this is equal to Ij sum over L of A 2L, A 12 plus 1 minus A 12 plus 1, A 12 divided by 2 minus H A 12 minus 1, A 2. Okay, here I forgot the I forgot the boundary terms. But we know how to treat them, so for a moment I'll just otherwise there's no time. I just consider the back part. Okay. Minus H, A12 minus 1, A12 minus A12, A12 minus 1 over 2. So now what is the block circular matrix? Oh, that's associated with this model. After you write this in this form. Now you see here why I told you that it's purely imaginary. There is an I here. And it's anti-symmetric. It's anti-symmetric. So if you write it, let's see, what's the structure of the matrix? So we have, here you have the term A2 that connects A3. So let's write it 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Then you have a term here which is 2 couples with 3. So 2 couples with 3, and it has a factor Ij over 2. Then you have on the other side a 3 that couples with 2, with a minus sign because it's anti-symmetric. So you have here minus Ij over 2. Then you have here this term which you have a 1 which coupled with 2, 1, 2, and then you have a minus Ijh over 2 here, and another here with a plus sign H over 2. There you have zeros, 0, 0. Then, well, we have just to remember that this matrix should be block circulant. So it means that this block should be equal to this one, minus Ijh over 2, Ijh over 2, 0, and so on and so forth. And then here all these blocks are 0, 0, 0, 0. You have to repeat this block here. So you have 0, 0, Ij over 2, 0. And here you have a 0 minus Ij over 2, 0, 0. So it's a block tridiagonal block matrix. And then, okay, here I am just ignore the boundary condition, but you know what to do. So in the end, you will find that here on the corner, you have this matrix, exactly this matrix. This can be a plus sign or minus sign, depending on in which sector you are. Okay. From here, you want to construct a symbol. How do you do? Well, simply the symbol is just the anti-Fourier transform of this. So you have to associate a phase to each block. The phase of this is 1. With this to associate the e to the ik, e to the 2ik, and so on. So the symbol in this case, okay, but now coefficient I operate convention, it should be this matrix here plus e to the maybe there is ik 0, 0, ij over 2, 0. This is the symbol of the Fourier model. Okay, you should check it because I'm not depending on the convention. That could be a plus sign or minus sign here. I hope that it's. I think it should be a plus sign. Given the symbol that we can construct all the conservation. So you see, it's once you know the result, once you know all the steps, it becomes extremely, so in the one line we solve the model, we found all the conservation rules for this model, which is remarkable. Because you could, I could have included here other terms, and I would have been able anyway to find a symbol in one line of the model. Okay, so with this I think I stop. Next time I will show you in this formalism how to compute a large time behavior. We will compare with the GGE, showing that it works. And then I think I would like to say something about pre-relaxation, pre-thermalization, and this is just next lecture. We won't be able to do more than this.
Okay, thank you very much.